Reading about how they used to navigate just brought home how scary it would have been. Once you get out there past Sunderland Point or past the south coast of Ireland and beyond, you're really at the mercy of winds and currents and things, and the navigators you had on board.
Join us for another episode of 100 Years, 100 Objects, Stories from Lancaster City Museums. I'm Rachel Roberts and I'm the Collections Registrar for Lancaster City Museums. In this series we're looking at 100 objects from Lancaster, Morecambe and the surrounding area to celebrate a century of our museums and to find out more about the past and how we relate to it now. Today's object is very simple in its construction. A series of wooden pieces attached together to form triangles and curves. But used correctly, it helps sailors navigate the world and open up new routes across the globe. Today's object is a backstaff. A backstaff is a navigational instrument which was used to take bearings from the sun. They were invented around 130 years before the more complex and arguably more familiar sextant. Our backstaff today is not 100% complete. It's formed of 4 straight and 3 curved pieces of wood, but would have originally had extra pieces which would have attached to the curves and one end, which were used to take the actual readings. There is one central piece of wood, which has 2 shorter pieces projecting from it at angles to form triangles, one of which is braced with the 4th straight piece to make it sturdier. Both triangles are enclosed at the wider end by the curved pieces of wood, which have engraved on them marks showing the degrees in an angle. Overall, it's about 65 centimetres long. Although the construction of the backstaff is quite simple, it needed to be highly accurate, and the user would need to have an in-depth knowledge of their craft in order to use it to navigate across vast stretches of ocean accurately. We spoke to Dr Joe Kinrade, a research fellow in the Space and Planetary Physics group at Lancaster University, about this intriguing and deceptively complex object and how it works.
So a backstaff, if you look at a photograph, is a couple of wooden triangles whacked together, basically. And it's actually a development of an earlier tool called a cross staff. And there's an even earlier tool than that, which the Arabian peoples used, called a kamal, I think. And that's essentially a piece of string and a block of wood. And all of these things are designed to let you take an accurate measurement of an angle between the sea horizon and a celestial body like a star or a planet or the moon or the sun. And once you have that, you can find, through a little bit of simple trigonometry, your latitude at sea. If you study the sky for a long time, stars start to rotate around a fixed point in the sky, which in the northern hemisphere is near Polaris, the pole star. And navigators have known this really for centuries and possibly even thousands of years. So that it was a pretty critical tool to take with you. You had to know your latitude, and they would have probably had at least some of the sea captains a book known as an ephemeride, which was a catalogue of latitudes of stars and the sun transits around the equator and up and down above the equator, put together by studying the stars over a long time. And that was a complicated thing to use, so early explorers in the sort of 1500s would have taken possibly an astronomer on board with them, maybe even an astrologer, because the position of the sun relating to the constellations was also an important thing to study. So somebody in the medieval times would have been used to saying things like, oh, that happened when the sun was in Cancer, rather than saying on the 21st of June. They would have been much more au fait with that kind of language. And certain cities would have had ephemeride catalogues. So people have been studying it from Lisbon or London separately, for example. So when you set out from one of these ports on a long voyage, you would mark your latitude of a fixed point in the sky, and then through some simple trig, you could have a rough estimate of longitude if you knew the distance to the other place as well. But longitude is a much more complicated problem than latitude. The height above the horizon you can think about as one side of a triangle. And at its very basic, it's Pythagoras' theory, a squared equals b squared plus c squared. And certain stars stay at fixed points in the sky relating to the equator. So if you know which those are, through long observation as the astronomers did, you can use these fixed points in the sky as a reference point. Sometimes they would also observe what they would call heavenly events, things like solar eclipses or lunar eclipses. Say if you took a measurement from one location of the point at which the moon rose on the horizon or the moon set on the horizon, and someone else did that at a different place, you could build up these comparison tables. If I could somehow talk to you back then on the other side of a continent and you could tell me the star above your head from another location, I could look at the direction of that star and I know that that's your direction. Also things like the sun. People have known for a long time that if you cast a shadow using the sun at noon, you can get north and south. And even today that we know in which direction the sun rises and sets. So that knowledge hasn't completely gone.
Navigation across the sea was such a crucial but perilous undertaking that even after the cross-staff, which had been around since antiquity, and the backstaff, which was invented in the 16th century, there was still an urgent need to continue to develop navigational techniques. Joe told us how these technologies developed after the backstaff.
It was quite a slow process. So between the 1700s, Portuguese were widely known as pioneers of this. They started to explore the coast of Africa. They hired French and Dutch and English navigators, and all this knowledge started to mix together. Quite a fast development was the sextant. Some clever people using some of Newton's physics about focusing light from different points onto one point got around the problem of motion at sea in terms of taking latitude measurements. So that was one of the big problems of holding the backstaff, was that you had to take measurements while you were swaying with the movement of the ocean. And the sextant could have used some optics to get around that, so it was much more accurate. Jumping forwards, measuring longitude became a big problem. Especially as voyages got longer, the world started to expand rapidly, the 1600s. And before that, longitude measurements, they would relied on something called dead reckoning, which is probably as scary as it sounds. Sailors were terrified of shipwrecks at night, so what they would do during the day would be to drop objects in the ocean and see how fast they drifted past the length of the ship. And they would do this, they would time it sometimes using sunglasses. Not very accurate, as you can imagine. So they would take multiple readings throughout the day, and there are reports of sailors taking their own measurements because of not trusting the navigator. They were so scared of being shipwrecked. And then they would see how far they drifted in an hour, maybe, and plot it on a chart. But obviously, a better solution was needed than that. So much later, maybe the 17th, 18th century, we start to think about timing. Measuring longitude at sea is different from latitude because you need some kind of reference point. Today we have Greenwich Meridian as a sort of fixed prime meridian longitude, but back then they didn't have anything like that. It was usually the capital city of the country of the navigator. The problem of clocks at sea is that you have swaying motion. Clocks back then were mechanical, so they relied on pendulum swinging, which didn't work well at sea. So there was a period of innovation, really through the instrument makers, where they tried to do things like reduce friction in the pendulum to make these clocks more accurate at sea. And eventually the Harrison Sea Clock won the Commission of Longitude Prize with the Royal Society, and that was a huge breakthrough for marine navigation, the ability to actually take an accurate time at sea. And then you can move right on through to GPS as essentially the next big step. People still carry sextants, by the way, on board Navy ships and things, just as a backup in case GPS possibly goes down. One of the big disadvantages of using the cross staff was that you had to actually sight the sun line. So sighting the angle of the sun along one of the sides of this cross staff would lead to blindness in one eye possibly. So I do like the idea that the picture we have of sea dogs with an eye patch, they were probably the navigator. It wasn't some kind of swashbuckling accident. And that was the big advantage actually of the backstaff. So somebody realised maybe 100 years later that you could turn around and it was a shadow cast by a notch on the backstaff that would give you that measurement angle of the star or the celestial body or the sun above the ocean, rather than sighting along a cross staff.
Some of Joe's work revolves around GPS technologies and their potential uses, so he went on to tell us how they work.
It's actually the simplest thing to explain compared to the stars and things, which obviously, as a person of today's world, I don't understand as well as they did back then. GPS basically works on the speed equals distance over time principle. If you have a signal sent at some time from multiple satellites, we know how fast the signal's travelling at the speed of light, and we can time when the signal was sent and when it was received with our receiver on the ground, and then you can know the distance. So when you have that distance built up from a constellation, 3 satellites gives you a position on a sphere, and 4 satellites will give you the altitude at that point on the sphere. So one thing you do need is super accurate clocks. So they're actually atomic clocks on board the Global Navigation System satellites. One thing that does worry countries and politicians and people using it to get to work is that the signals currently are free, which is a fantastic thing, but they are susceptible to potentially drastic space weather events. And these things are rare. The last recorded super event was called the Carrington event in 1859, and that caused things like the auroras to really flare and be seen over southern Europe even. And if that happened today, we don't really know how the space satellites would cope with it. And it's actually radiation damage that would come in from the solar wind. We're very reliant on GNSS systems these days. Every bank transaction you have at a cash machine is time tagged. Deployment of ambulance and fire services and police services is really inherent in our society. And something I like to think about is actually, a lot of us use it to navigate, but it kind of takes us away a little bit from that sort of ancestral sense of direction and navigation that we have in our brains already. The brain has very different techniques to deal with navigation. So as soon as you walk outside, you're subconsciously seeing anchor points on the skyline, whether that be a church spire or a river. Your brain takes that as a reference point. And then neurons start to fire as you're walking around to actually have different synaptic responses for If we're walking next to an edge or a boundary, that kind of maps as a linear feature in our brain. Whereas GPS, we sort of are a slave to it almost. We get in our car, we put GPS on, and then we just go from A to B. But actually our brain isn't noticing where we're going. So I do still like to not use it occasionally. I like maps.
Joe's work also focuses on auroras and how they interact with our modern GPS systems. He explained what he has found while working on this topic.
So the auroras, they're a spectacular light phenomenon in the night sky. You might have been lucky enough to see them. I myself have never seen them in person, despite studying them. It's crazy, right? We are sat in almost a constant stream of radiation that's boiled off the surface of the sun, and we refer to this as the solar wind. And we're largely protected by our magnetic field. So most of us are aware that we have a magnetic field at Earth, and people have been using that to navigate as well with compass needles since the early Chinese dynasties. But this magnetic field deflects a lot of that solar radiation away from us, except at the polar regions where the sort of funnel of the magnetic field comes down and gives access to the lower atmosphere to this solar radiation. And when these energetic particles hit the neutral atmosphere, so the oxygen and the nitrogen particles that are floating around up there, they get charged. And when that energy eventually gets released, it's released as photons of light, which is what the aurora are. So it's actually a relaxation of the energy that's been put into the atmosphere by the solar wind. And the different colours correspond to different altitudes and where there's different mixing with the oxygen. So oxygen tends to be green lines, the greener side of the emission, and the nitrogen-based lines is the reddy sort of purpley colour, which can happen at a bit higher altitudes. People have noticed the auroras as long as people have been recording observations of the night sky. You can go back to the Vikings who thought that gods were warring or the sky was on fire, things like that. In terms of how they affect navigation, it's difficult to say. In terms of navigating, certainly on a cloudy night, they wouldn't have been able to see the stars, which would have been pretty scary when you think about it. They probably had to go back to something like Dead Reckoning at night, probably a sleepless night for the sailors. But when the stars were visible, the aurora possibly would have been at northern or southern high latitudes, and certainly they would have been awestruck by it. Explanations for what the aurora were, they weren't really confirmed until the 60s in the dawn of the satellite age, when we actually flew rockets through those kind of altitudes. So before then, theories about what auroras were different across different cultures. In terms of their navigation, if you've been lucky enough to see the auroras, they're actually quite a dim event, and a lot of the photographs that you see are kind of long time exposures making them look brighter. On occasion you do get really strong storms, geomagnetic storms, where you do get really bright, fantastic shows in the night sky. But for the sailors, they probably will still have been able to see the stars, and the moon certainly, through the auroras at night. The light itself, the actual photons, it is not what affects a travelling radio wave, something like a GPS signal that is a radio wave. But we can use the lights of the auroras to locate where there's turbulence in the atmosphere. So if you look at a star in the night sky, particularly on like a warm evening, you can see the star twinkling. That's not the star changing, it's actually just the ray path of the light going through turbulence, so tides and scattering of small structures of electrons in the atmosphere. And that's the same thing that happens to GPS signals. You won't really notice it on your phone, so your phone has a tiny, we call it a patch antenna. And the kind of navigation we do with Google or with WhatsApp locations and things is not really going to be affected because there's software corrections that happen. Within a millimetre you can actually get that accuracy with GPS systems and GNSS systems. The kind of navigation that's affected by the auroras and this kind of turbulence in the atmosphere is the high precision stuff. So actually the atmosphere is still the largest source of error in using GNSS or GPS systems. Things like positioning drill bits on the ocean floor, very accurate timing for things like tracking glacial movement over a century even. So if you have a big antenna on the ground with a special receiver about the size of a shoebox, we call them geodetic receivers, but they're just really very precise versions of the ones we have on our phones. You can track that sort of stuff over time. If you don't take account of the atmospheric correction, which is the similar phenomenon that's causing the auroras, your position can drift over time. So it's really important to consider that sort of thing. And one of my main experiments in my study was putting GPS receivers across Antarctica. And what we did was have a camera co-located with this GPS antenna at the South Pole, and we would track the GPS satellites through the auroras and monitor the brightness of the aurora around that ray path, and it correlated really well. So that was actually a question that one of the pilots asked us. He said, is my navigation being affected by the auroras? And the answer is to some extent yes, and it's actually why we still can't land commercial aircraft automatically without a pilot, because we just can't rely on that atmospheric correction being good enough for the safety of human life. So the atmosphere still plays a part, as it did back through the centuries, of navigating.
Do auroras only happen on Earth, or can they be found elsewhere in the solar system?
At Earth, the auroras are a product of us being close to the sun, and we're sat in that stream of radiation. At places like the gas giants with Jupiter and Saturn, the story's a bit different. They have very big, very strong magnetic fields, and they're further from the sun. The solar wind still impacts those planets, but what we find that happens is that we've discovered they're moons. So there's volcanic moons that orbit Saturn and Jupiter. Saturn has Enceladus, which is this tiny ice moon, maybe has a sub-ice crust ocean, and that actually has ice volcanoes on the surface. they spew water out into the space around the planet. And as that new mass, this water mass that goes in orbit around the planet, that drives huge electrical current systems that map into the atmosphere of Saturn, which is largely made of hydrogen, and makes ultraviolet auroras, which we can detect with things like the Hubble telescope and the Cassini satellite that was there for about 14 years. That's something I work on. At Jupiter is a similar story, except there's sulfuric volcanoes on Io, and they load the magnetic field around the planet with mass as well, and a similar thing happens, and Jupiter has the brightest UV auroras in the solar system. There are also visible auroras at Saturn, which are pinky-purple, but they've been rarely detected. There's also very dim auroras at Mars, because Mars doesn't really have much of a magnetic field left. It's what we call a remnant or a crustal field. But interaction with the solar wind there, with thin bits of atmosphere at Mars, do possibly produce dim auroras. And the ice giants, which as they're referred to at Neptune and Uranus, they also potentially have very dim auroras that have possibly been detected with Hubble. And James Webb may detect infrared auroras as well as some of these planets. We saw infrared auroras at Jupiter and Saturn as well. But yeah, certainly different planets have auroras, and it's a useful way of looking at something very far away, but using the auroras as a sort of footprint or a fingerprint to tell what's happening around the planet in terms of its space environment.
Before he left, Joe told us what the Backstaff meant to him as someone who works on 21st century navigational technology.
I think it's been really interesting reading about it, because obviously Lancaster has such a rich maritime history, and I think people tend to forget walking around the city that tall ships used to be just up as far as the Maritime Museum here. Reading about how they used to navigate just brought home how scary it would have been. Once you get out there past Sunderland Point or past the south coast of Ireland and beyond, you're really at the mercy of winds and currents and things, and the navigators you had on board and the ability to do that. So it really sort of brought that alive for me, reading about this sort of stuff.
Thank you so much for navigating your way to this episode of 100 Years, 100 Objects. We hope you will find us again soon for another episode where we discuss everything from watercolours to water courses.